Honored to have Alex Simpson, who will talk to us about three toposes for probability and randomness. So Alex, take it away. Thanks.
Okay, thank you very much, Evan. And I'd like to thank you for the invitation, particularly Valeria for inviting me to speak here. Um, so what I'm going to speak about is a program of work that I've been doing for actually rather a long time, 12 and a half years, essentially. And I can be very sure about that because I can pinpoint the start of this program of research rather precisely because it originates from some conversations I had with Dana Scott at the Lorentz Institute in Leiden in the autumn of 2011. So it was very nice just now to see that Dana Scott's in the audience today, so Dana can see what has happened to this conversation that these conversations that we had 12 and a half years ago. So it's been a long program of research. I've presented many talks on it over the years. I've always talked about specific aspects. So what I thought I would do today is rather try to give an overview of the program of research as a whole, which seemed a natural thing to do because this is the Topos Institute Colloquium, and the connecting thread between the different strands of research that I'm going to talk about is that there are essentially three different things I'm going to talk about, but each one is based on a topos, and the toposes are related to each other. So that's the toposes are all to do with probability and randomness, and the only problem I found in preparing this work for presentation just now is that actually, in order to get through three toposes in the time available, it's going to really be a whirlwind tour. So I apologize in advance that some parts of this are probably going to be a little bit impressionistic, and sometimes it would feel more natural to spend a bit more time on some things than I'm going to be able to. But anyway, we'll take it for what it is. And you know, three toposes, it's roughly 15 minutes per topos, but I think we're going to spend more time on the first one and then kind of gradually less time as we go along. Anyway, let me just close my Zoom controls if I can. And I want to get rid of some. Okay, I don't seem to be able to get rid of, anyway, something you can't see, doesn't matter, let's page forwards. So we're going to start with topos 1. So the toposes are to do with probability and randomness. Topos 1 is about probability. So what do I mean? Well, I think the best way into this topos is the following observation, which is now reasonably well known, which is that random variables, if you view them in an appropriate way, form a sheaf. So let's have a look at this. So what is a random variable? Well, a random variable is normally a random variable x is, in normal mathematics, a measurable function from a sample space of possible probabilistic outcomes to the value space, sort of typically the real numbers, for example. So here we have such a random variable x. So that's defined over a particular sample space, but it's often useful in mathematics to change the sample space. And one often changes the sample space by changing the random variable along, say, a projection into the original sample space from a larger sample space that gives one more probabilistic possibilities, so to speak. So, for example, a projection down from some larger space here. And if we have such a projection of sample spaces, then, and I do have some annoying thing up here that I'm sorry that I don't seem to be. Okay, so yeah, I managed to get rid of it. So if we have such a picture, then of course we have an obvious random variable defined on the larger sample space, which is simply the composition of x with the translation function p between the projection function p between the sample spaces, which I'm going to write like this, x dot p, to emphasize that this is we're thinking of this as an action of a pre-sheaf. We're looking at random variables over the sample space omega, and there's a contravariant function or functor mapping random variables over the sample space omega. We've got to map into omega, and by reindexing x along p, by composing it, we get a random variable from the larger sample space omega prime. So working in the opposite contravariant direction to the direction of p. Now, when I said that omega prime is a larger sample space than omega, actually, all we really need to have to get this picture to work is that we've got two sufficiently nicely behaved sample spaces, and that p is what's called a measure preserving or probability preserving function between them. Because if p preserves probability, the reindexed random variable will essentially be the same random variable with the same law as the original random variable. And moreover, if the sample spaces are sufficiently nice, if p preserves probability, then the image of omega prime under p will be a measure one, a probability one subset of the sample space omega. So p is, in a sense, essentially surjective. So as long as p is measure preserving, we can kind of view p as a function that expands on the possibilities available in omega by giving you a greater multiplicity of possibilities in the sample space omega prime. So that's the pre-sheaf property. We reindex x to get on omega to get a random variable on omega prime. But there's a corresponding sheaf property that goes in the other direction. And the sheaf property is as follows. So we've got the same picture here that omega prime is projecting down to omega. Suppose we have a random variable y on omega prime that enjoys the property that it doesn't make any use of the additional probabilistic possibilities that are available in omega prime beyond those in omega. So mathematically, one might say this, a property that would give this is that the random variable y is almost surely constant on fibers of p, which one can make precise in various ways, but I'm not going to go into that. We'll just work with it intuitively for the moment. So if this is the case that y is on each fiber of p, so for each sample point, little omega in omega, we have the fiber above it of sample points up here that get mapped into little omega. Y is almost surely constant on those. We get a map from omega, from the lower sample space omega into the real numbers here, defined by mapping a sample point little omega here to the single value that the fiber of little omega up here is almost surely constantly mapped onto. And as long as we're sufficiently identifying random variables up to almost sure equality, what we get here is that there exists a unique random variable x from omega to r such that, so there's an x here such that y is the reindexing of x along p, at least up to almost sure equality. So essentially, here we're saying we can extend a random variable to a larger sample space. Here we're saying if we have a random variable in a larger sample space that doesn't depend on any of the additional possibilities that are available in the larger sample space, we can restrict it to a unique random variable on the smaller sample space. And this is a sheaf property because there's a Grothendieck topology at work here, known as the atomic Grothendieck topology, on a sufficiently nice category of sample spaces. And this property exactly says that random variables form a sheaf with respect to the atomic Grothendieck topology. So what we're going to do is make this precise by looking at now at a nice category of sample spaces and looking at the sheaves on the nice category of sample spaces. So a nice category of sample spaces is, well, we want, by nice, I mean sample spaces that have good mathematical properties. So a well-known nice category of sample spaces are what are called standard Borel probability spaces. So standard Borel spaces with a probability measure, and then as before, as on the previous slide, we're looking at measure preserving functions between them. For the purposes of this talk, it doesn't really matter what a standard Borel probability space is. All that we need to know is that it's a category of mathematically this is a category of mathematically well-behaved sample spaces. And as on the previous slide, you could look at measure preserving functions as morphisms, or you could look at measure preserving functions, and I'm going to write mod 0 here, which means modulo a null set, or identifying functions up to almost sure equality. So one could look at this quotient category as well as morphisms. In both cases, the categories satisfy the condition needed for the atomic Grothendieck topology to exist. So one can look at the categories of atomic sheaves, which I'm going to write like this, sheaves atomic for either of these two categories. And it turns out it doesn't matter which of the two categories you choose. So those two toposes of sheaves are equivalent. But for definiteness in this talk, I'm going to define my topos of probability sheaves to be the sheaves over these nice sample spaces where we have measure preserving functions and we identify those functions up to almost sure equality of functions. Okay, so if we're in this category, do random variables form a sheaf? Well, indeed they do form a sheaf, but we don't have just a sheaf for real valued random variables. We have a sheaf of random variables for any suitable value space of random variables. And once again, we want to, so random variables you can in general value in a measurable space. We want, again, a good collection of measurable spaces. And as with the sample spaces, we're going to take standard Borel spaces as our good collection of measurable spaces. And so for any standard Borel space, a good notion of value space for random variables, we get a sheaf of random variables where the random, so for the sample, for the value space A, the sheaf of random variables is going to be a pre-sheaf, so it's got a contravariant functor from our sample spaces interset that on any sample space omega is defined to be the random variables from omega into A, so the measurable functions from omega to A. We need to identify up to almost sure equality. And just as on the first slide, the reindexing of random variables, the contravariant functorial action is given by composition of here with using composition of equivalence classes. Okay, so random variables form a sheaf for any suitably nice space of values of the random variables. Kind of the main thing I wanted to do with this topos was to then we've got a nice mathematical world, in a sense, a topos in which we have an object of random variables for each suitable space of values for the random variables. And it seemed a good environment for essentially teasing out the structural mathematical properties of random variables, to basically look at what are the properties of random variables that allow us to reason with random variables. Are there some category theoretic properties that explain the mathematical ways that one reasons with random variables? And indeed there are. And so the first thing is that the mapping from a value space to random variables is functorial. So that's very straightforward. We have the object action I gave before on the value spaces actually maps any standard Borel space, is a functor from standard Borel space to the topos of probability sheaves. And this functor is faithful. It's very far from being full, but I'll leave that as an aside for now. Anyway, it's a faithful functor, and it enjoys the important property of preserving countable limits. And just as a remark that actually this domain category, which I'm considering as standard Borel spaces and measurable functions, the usual category, can actually be expanded to universally measurable functions and still faithfully lands in the category of probability sheaves. But that gets a bit more technical. So to keep things simple, let's just work with standard Borel spaces as nice value spaces in this talk. So we have a functor of random variables. There's another important functor from our value spaces as well into probability sheaves, and that's the functor that for any value space A assigns the set of probability measures on the value space A. So the probability measures are probability. We have a value space which is a standard Borel space, so that comes with a sigma algebra. I'm going to loosely refer to that sigma algebra as the Borel subsets of A. So the probability measure is a measure defined on the Borel subsets of the value of the value space A, and the functor simply maps every value space, so every standard Borel space, to the set of all probability measures. Well, that gives us a set, but we can convert it to a probability sheaf by just taking the discrete pre-sheaf, which is a sheaf for this, which is a sheaf for the atomic topology. And this functor is again faithful, and it also satisfies, it doesn't preserve limits, but it satisfies one nice preservation property, which is tautness, which has been, I think, a subject of at least two recent Topos colloquia, one by Bob Paré and another by Eugenio Moggi recently. I'm not going to dwell on this property, but just to register that this functor enjoys this property. And putting the two functors together, the random variable functor and the distribution functor, the one that maps the value space to the set of all probability measures, very important structure we have is a natural transformation from the random variable to the distribution functor. And what this does is, given a random variable x, it assigns to the random variable, it maps that random variable to the probability measure, which is called the law of x, or the probability distribution of x. So the important point on this slide is that mapping from a random variable to its probability distribution, so its measure, is a natural transformation. Moreover, this natural transformation is also taught in the sense that was discussed in the talks of Bob Paré and Eugenio Moggi. Eugenio's talk was very recently. So again, I'm not going to dwell on that, but it's an important property to flag here. So my Zoom controls are hiding the title, so I just need to, I keep on closing them, but they keep on popping up again. So hang on a second while I just, right. Okay, so once we've got this structure, these two functors and the natural transformation between them, what we can do is we can use the internal logic of the topos to define relations of probability, to define concepts of probabilistic interest, for example, relations between random variables. So the internal logic of this topos is very nice because it's an atomic topos. So all atomic topos is a Boolean, so that means the internal logic here is classical. So we've got a classical logic, and within that classical logic, if we're given two random variables over the same value space A, then we have two important equivalence relations on them. The one is the equivalence relation known as equality and distribution, which just says they have the same probability law. So we can express that very easily using our natural transformation with the probability law. Just the probability law of x is equal to the probability law of y. The other is the slightly more subtle equivalence relation of two random variables being equal almost surely. So we can express that using the tools we've got available by saying, well, we're going to consider the probability law of the joint probability joint probability distribution given by the random variables x, y together. And we can do that because we've got the product preservation of the random variable functor. So the pair xy would normally land in the product of random variables of A with itself, but by product preservation, that's the same thing as giving a random variable on A squared. And so we can look at the probability law of the joint law of X and Y and ask for the probability of that pair of random variables landing in the diagonal to be 1. So that's saying they're almost surely equal. Now, someone who's been paying attention might say, aha, but when you defined your sheaf of random variables, didn't you identify random variables up to almost sure equality? So isn't this just going to be equality between random variables? And indeed it is. So in this topos, this is equality between random variables. But in fact, this happens for a rather nice reason, which is it follows axiomatically from the structure we've got so far. And it's actually a consequence of the tautness property of the natural transformation that finds the probability law. So here we've got the almost sure equality flagged here, and the proposition is that because of the tautness of this probability law natural transformation, almost sure equality is the same as equality of random variables. I view this as a nice kind of abstractness property of the general picture we have, because somehow, in a sense, almost sure equality is the right conceptual notion of equality between random variables, and it's nice that that falls out of the category theoretic laws. Another important concept relation between random variables is, of course, the independence relation. A lot of people view this as the most important relation in probability theory. And we can again formulate that using joint distribution. So basically, this is saying for all Borel subsets of A and Borel S and Borel subsets of B, T, the probability of the joint variables landing in the rectangle is the product of each variable separately landing in its component, in its edge. And once we've got equality in law, equality in distribution, so which I was using this symbol for, and independence, there are two important logical laws to flag in this topos of probability sheaves. The first one I call the invariance principle. So this is saying if we have a subsheaf of one of these sheaves of random variables, so a subsheaf, we can view this as a property we can describe in the internal logic, for example, that depends only on the one random variable. So it's only free variable, if you like, is the random variable that we're forming a property of. And if we have such a property in the internal logic that just has one random variable as its free variable, then the following principle holds, which is for any two random variables of the appropriate type, if they're equal in distribution, then, and if the property phi holds for X, then it also holds for Y. So equality in distribution has a substitutivity property like equality itself, as long as one's talking about properties that are actual subsheaves of the sheaf that you're talking about. So logically speaking, properties that only contain one free random variable. And this is another nice abstractness property of the scenario, because it's essentially saying in this world, in this topos world for random variables, one cannot, in the internal logic, formulate any property that does something nasty, so distinguishes between two random variables in some non-probabilistic, meaningful way. The only way we can distinguish between random variables is by respecting the law of random variables. And the second principle I want to flag is what I call the independence principle. And that says there exists an inexhaustible supply of independent random variables. So whenever we have a random variable X and a random variable Y, we can find a Z, which is another copy of X because it's equal in distribution to the random variable Z, but enjoys the property that it's independent from Y. So these two laws are actually studied in a paper that is going to appear in LIX this year. I'll talk about that a little bit later. They're rather fundamental to the reasoning that one does in this topos about probability. When I wrote the slides, I was going to give one example of the reasoning about probability, but I realized at the time that I wasn't going to have time to do it. So I'm going to skip the next few slides and just say very briefly what I'm doing. But I left the slides in because I thought it would be nice to have them published afterwards. So in the next bit, we're going to use this independence principle together with the axiom of countable dependent choice, which also holds in the topos. And this is the outline of the proof that the axiom of dependent choice holds in the topos to construct what are called in probability IID sequences. So these are infinite sequences of independent and identically distributed random variables. And the proposition here says, if you've got any random variable x, then we can find an infinite sequence of random variables such that all the random variables in the sequence are equidistributed with x, but it's a sequence of independent random variables. And the proof, which I won't talk you through, is essentially just applying this independence principle that always gives us a new independent random variable together with the axiom of dependent choice to get the sequence at the end. But once we've got a sequence of random variables, there's something else rather important that we can do, which is, so the sequence of random variables is in this exponential, but by countable product preservation, that's isomorphic to a random variable over sequences. And using that, we can express important properties like, for example, I've written here the Kolmogorov zero-1 law for tail sets, or for example, the strong law of large numbers, which is about limiting properties of infinite sequences of values in A. So this equivalence of countable product preservation is really important for expressing such things. I'm going to give some reference at the end to where you can find out more about this. So I'm not going to dwell more on that now, but I do want to flag an issue that arises. So essentially, here we're dealing with countable sequences. Countable sequences work well, and that means also if we tried to formalize stochastic processes, everything would work well for discrete time stochastic processes. But when we get to continuous time, the current setting is a bit more problematic. So for example, if we wanted to express some properties of a random variable over trajectories in the real numbers, say on non-negative time values, well, we'd have to say what we mean by this sheaf of random variables. So in order to have this sheaf, well, the only way we had of getting these sheaves was to have a standard Borel space here, a good value space. So we'd have to construe this as a standard Borel space, which we can do because we could say, make this the continuous functions, and we could put the compact open topology on it and consider the Borel sets there, and then we do get a standard Borel space. But on the other hand, from a probabilistic point of view, this is all very awkward because it's kind of pre-commitment to continuous processes and a particular choice of sigma-algebra, and none of the sort of elegant way that one would like to do continuous stochastic process theory. So everything's a little bit encumbered by having to fix on standard Borel spaces and sigma-algebras. So we'll pause there and end our topos 1. And we've got, so that took half an hour, but there was a bit of time, so basically 25 minutes. So the next two toposes are going to have to be much quicker. But the second topos, we're going to move from probability, which was the subject of the first topos, to randomness. Well, some people might think probability and randomness are synonymous.
Yeah.
Other people, probability, it's clear what it means, but randomness is not clear what it means. All sorts of nonsense has been written about randomness. So what do we mean by randomness? Well, I'm going to distinguish between randomness and probability by distinguishing between random variables, which we have for probability, and what I'm going to call random elements, which is different from a random variable in the following sense. What I call a random element is an A-valued random element, if we're again having some nice value space A, rather than being something that can vary when we sample it according to a probability law. So random variables can vary. A random element is a fixed element of the value space A. but a fixed element that we get by sampling a random variable. And of course, the classic example of this is the notion of random sequences, infinite random sequences generated via an infinite sequence of fair coin tosses. So, for example, if we consider the following two infinite sequences, the first one is just a repeated sequence of 0 1s, 0 1 0 1 0 1 ad infinitum. According to ordinary mathematics, this is just as random as any other sequence. Any infinite sequence could be the outcome of sampling a fair sequence of coin tosses. Just any sequence has probability 0 of arising, and therefore, it almost surely doesn't arise. But I want to move to a setting where this most definitely is not random. I mean, it doesn't look random. On the other hand, the second infinite sequence is random. Well, how do we know that? Well, we know it because I'm telling you that it's random. We actually don't know what the dot dot dots are here. I mean, it's some continuation of that. And because it's random, it would be very hard for me to tell you what the dot dot dots are, except one by kind of generating them as they go along. But anyway, I want to be in a setting where there exist such random sequences, and this first sequence that very definitely has a pattern is definitely not random. Now, there's a very naive way of approaching randomness that doesn't work, which is to say that an infinite sequence would be random if we've got a random sequence, we can think of the following. Let's test it with a property that has a probability 1 of success. So we're testing the sequence S. And if S is a random sequence, then, well, almost surely it will satisfy that test. So it would be nice to say, well, so if we've got a genuine random sequence, it's going to satisfy all probability 1 tests. But the problem is that almost sure is not sure. And of course, no sequence is naively random in this sense, because you can simply take a test that just takes all possible sequences but throws away the one sequence that you're testing for. And that is, of course, still a probability 1 set, but it excludes the sequence that you're testing for. So naive randomness doesn't work, and there are very good mathematical approaches to randomness that circumvent that. For example, there's a huge field of algorithmic randomness that studies concepts like Martin-Löf randomness, where one says, okay, well, I'll deal with this by making sure that the testable property T is given by some sort of computability theoretic considerations, and that avoids this problem here. Also in set theory, random sequences are important in various model constructions and independence results, and there, so Solovey's idea, I think, when this was introduced, was that you can define a sequence to be random if it satisfies this property with respect to those probability 1 sets T that are definable in some starting countable base model of set theory that you start with. Okay, so these are approaches to getting a consistent theory of randomness. I want to be a bit more naive than this, and what I want to do is say, well, okay, naive randomness doesn't work, but it still suggests something, and it suggests a good notion of randomness preserving function between sample spaces. So before we were considering probability preserving or measure preserving functions between sample spaces, which preserve all probability, the idea of a randomness preserving function is that if you generated a random element of omega prime, then you apply f to it and you get back a random element of omega. And the naive definition suggests that a sensible notion of randomness preserving is simply one weakens measure preserving from measure preserving is the inverse image preserves the measure of Borel sets. And we weaken that to inverse image preserves measure 1 sets, those sets that we use as the tests in the naive definition of randomness. And this gives us a perfectly good notion of randomness preserving map. So inverse image preserves probability 1 sets, or equivalently, inverse image preserves probability 0 sets. And I should say that I first extracted this as a good notion of randomness preserving by reading I don't know how explicit it was, but I got to this by reading the works of Michael van Lambalchen. And so I owe this concept to my reading of his works, so to speak. Anyway, so we have now a new category of morphisms between well-behaved sample spaces. And the idea is, well, we're going to simply consider these as categories, modify the site that we're using to construct the topos, using randomness preserving functions instead of measure zero preserving functions. Again, we can either have the functions themselves, or we can identify them up to almost sure equality. And what happens is this carries a natural Grothendieck topology. And if we consider the category of sheaves over this, rather miraculously, it turns out to have a very good theory of random elements in it. So the topology consists of countable families. So we want to cut, this is a Grothendieck topology, or a coverage. So we want to cover a sample space by a family of maps. We consider countable families of maps that are covering in the sense that the union of their images has measure one in the destination sample space. Actually, the definition of image is a bit subtle, but I don't want to spend time on that now. What's important is that we have this countable covering family, these countable covering families. They form a Grothendieck topology, so we can consider sheaves for this countable cover topology. And what I call the random topos is defined by taking sheaves for this countable cover topology. Once again, it doesn't matter if we consider sheaves for the category with maps identified almost surely, or maps, or just the randomness preserving functions themselves. So that's the random topos. Sheaves for the countable cover topology on the category of randomness preserving functions. And once again, it's a very nice topos. It's once again a Boolean topos. In this case, that happens because the countable cover topology turns out to be what's called the dense topology, which always gives you a Boolean topos. Once again, dependent choice holds. Because we're in a Boolean topos, the subobject classifier is the Booleans 1 plus 1, so I'm going to call it 2. One normally calls the subobject classifier omega in a topos, but I've been using omega for sample spaces, and it would have got very confusing the next line if I'd used omega also for the subobject classifier. So the Booleans here, 1 plus 1, 2, which is the subobject classifier. This is the pre-sheaf, which is a sheaf, which is defined on a sample space omega. It is the set of Borel measurable subsets of omega. Modulo 0 means here identified up to null symmetric difference. And for those who know about it, they will know that about such things, they will know that this is a measure algebra, something called a measure algebra. The real numbers, well, the real numbers object defined on omega is the space of measurable functions from the sample space omega into the reals, again, modulo null sets, or modulo almost sure equality. The space of infinite sequences is, again, measurable functions from omega into the space of infinite sequence, modulo null set. But now we get to the core reason for looking at this topos. We have a good notion of random sequence in this topos. So the sheaf of random sequences, well, what we want is, so this is going to be the random sequences, the random bit sequences. So we want, obviously, this is a subset of the sheaf of all sequences defined above. So we want it to be those sequences that, so essentially, we want this to be random elements given parametrically in a randomly generated element of the sample space. So there's a very natural way of saying that. Well, to make sure we get, if we feed in a randomly generated, if we sample a randomly generated element from the sample space, we want to make sure that we get a random sequence of 2 to the n out as a result? Well, we'll get that if we have rather than the set of all measurable subfunctions, the set of randomness preserving functions from the sample space into the space of sequences with the uniform probability measure, the usual coin toss measure. And that's what it is. That's the canonical set of random sequences in this topos. And just to remark, it's a representable. So it's the representable of the sample space of the sample space given by a uniform randomly generated sequence. But what's really nice about this topos is that we then have the following internal characterization of random sequences, which corrects, in what I think is a very, very intuitive way, the naive definition of random sequence. So internally in R, we can define the set of random sequences as the set of all sequences that enjoy the property that for all test sets of sequences, if the test set has measure 1, then indeed the sequence will belong to the test set as long as the test set is generated independently from the sequence S. So that was the problem with the inconsistency of the naive notion of randomness. There we used the test sequence, the sequence we were testing for, the sequence itself to generate the test sequence. You're not allowed to do that. You have to keep the sequence independent from the test set. So what does this independence mean? Well, that's a whole story in itself. But just to say very briefly, this topos has a primitive relation of independence on it, which is related to the day convolution tensor product. And that's all I'm going to say for it in this talk. But what one gets from this, oh, I did want to say one other thing there. So the other thing is, you might notice here that also I wasn't very careful in quantifying over the test sets. I just said for all test sets of the reals. And so what do I mean by the measure of the test set, the probability of the test set being 1? Shouldn't I restrict to some measurable test sets here? But actually we don't need to because of the following theorem. Sorry, I need to hide my Zoom controls, which have popped up again. Which is that internally in the random topos, there actually exists a measure on all subsets of infinite sequences that extends the uniform Borel measure. So the usual Borel measure for coin toss measure extends to all subsets. And moreover, it does so in a translation invariant way. Here, the relevant notion of translation is the bitwise exclusive OR operation, which is the appropriate compact group action on is the appropriate compact group structure on the set of infinite sequences here. So I actually last talked about this topos 10 years ago. So there's been a very long pause in public talking about this topos. I last talked about it at Pino Rossellini's 60th birthday party in Palermo in, I think, September or October 10 years ago, 2014. In that talk, I gave a rather roundabout outline of the proof of this theorem using a closed the day closed structure on the random topos. Even though there isn't much time, I do want to give you just a little idea of how this works, because it's actually a very simple, direct argument. And I think we might just do the third topos very, very quickly, because I think I do want to give just a little an idea of how we construct this measure defined on all subsets. So we want to define a measure defined on all subsets of on all sets of sequences. So let T be a set of sequences in the topos, so an element of the power set, and because this is a sheaf, hence a pre-sheaf, and being an element, it needs to be an element at some sample space omega. So the power set of x is, of course, 2 to the x. So this is isomorphic to 2 to the 2 to the n. So we can consider t as a function from sequences to truth values at sample space omega. Because it's a pre-sheaf, we can re-index along any map into the sample space. So let's give ourselves a fresh random sequence by producting the sample space with the uniform probability measure on infinite sequences, and then we have the first projection into omega, which is measure preserving, hence randomness preserving. So t re-indexes to a function on this expanded sample space. So we now want to apply this re-indexed t to a particular infinite sequence. For the particular infinite sequence, well, we need to consider a sequence over that expanded sample space. And there's an obvious such sequence, which is this was the sample space. We simply consider the second projection. So here we've got the probability is omega together with the random variable that gives us a infinite coin toss, and we simply project that to the infinite coin toss. So it's a generic random sequence, if you like. So then applying t to this generic infinite sequence, we get a truth value at that new sample space. But by our characterization of truth values as Borel sets up to null symmetric difference, that's a Borel subset of the product space omega times infinite sequences. So it looks something like this yellow blob here in this product space of omega times infinite sequences. What we want to get is a real value in 0, 1, which is going to be the measure of the set. So that's a function from omega into 0, 1, again, modulo null sets. And we have an obvious such function, which is to map any sample space little omega to the probability of landing in the vertical bar above little omega here. And that's it. That's the construction of lambda, and actually the proof that this is a translation invariant measure extending the uniform Borel measure is really easy. Every single statement there is very straightforward. So more generally, we don't just have that for the fair coin toss measure on infinite sequences. We have it for arbitrary Borel probability measures. And here's a rather complicated theorem that says the sense in which we have it. But I'm going to skip that to get to the third topos, in which we go back to probability again. So time is running out, but it doesn't matter so much because this topos is really rather easy to tell you about by this stage. Because what is this topos? Well, it's the first topos we had. It's the topos of probability sheaves, only we define the topos of probability sheaves in the random topos R. So it's the relative topos of probability sheaves relative to the random topos R. And in doing that, well, we still have a random variables endofunctor, but now we still have a random variables functor, but now rather nicely, rather than being a functor from the category of standard Borel spaces for the value spaces, it's just an endofunctor on the topos itself. Any set is a suitable value space for a random variable, and that's okay because all sets are measurable, so we can kind of deal with the issues that arise, and that gives rise to a functor. So I'm going to publish my slides, so the definitions will be on the slides, but I'll just stick to the story. Again, we have the law of a random variable, and again, this is defined arbitrary sets, and now the law is maps to any set A, the set of all what I call power set probability measures, so measures defined on the power set of A. And again, we have the natural transformation that maps a random variable to its law. Once again, this is a Boolean topos, that the functors are faithful, the natural transformation is taught, the independence principle and invariance principle apply, dependent choice applies, and this topos supports the development of an axiomatic synthetic probability theory based on the random variable functor. I've actually talked about this in the past, and I'm going to give a link to a talk on that at the end. Just to wrap up, so what we gain in this new version of the topos of probability sheaves relative to the random topos is that random variables can be valued in arbitrary sets and their laws are power set measures. This means we can avoid many of the measurability issues in probability theory. So for example, one can define stochastic processes very nicely. So one could define stochastic processes as simply a function space from times to random variables, or what we were trying to do before, random variables over the function space from times to reals, over the space of all their trajectories. Very nicely, these two definitions correspond to probabilistically meaningful definitions of processes. The first one gives processes up to being modifications of one another, as probability theorists call them, and the second one gives processes up to indistinguishability. Okay, so that was 3 toposes. There's actually a 4th topos, which is not my topos. It's a very nice topos related to the previous 3 by the text that I've said here, that appears in a paper that's another LIX paper from this year with several authors, John Lee, Amal Ahmed, and various co-authors here. So I just wanted to flag that there's, if you found these 3 toposes interesting, or anyway, it's nice to look at toposes for probability theory. Here's a 4th topos to look at. Reference material. Well, I've been doing this work for a long time. Sadly, not much of it has been written up so far. It's a rather huge program, but the first paper on it, well, there are some like little papers, but the first main paper on it has just been accepted at LIX this year. So this is on the archive. So let me refer you to that. And here are some references to talks I have given that are recorded and online available on different aspects. So yeah, sorry for slightly overrunning, and that's the end. And rushing.
That's great. Thank you so much, Alex. That was a very, very interesting talk. So maybe we'll open it up for questions now. I have a few questions I could ask, but first, let's see maybe if there's anyone from the audience, if you want to raise your hand. Kevin, go for
it. Sure. Thanks so much, Alex. A lot of great stuff. I want to just ask about externalization of results in these toposes back to traditional probability theory. Like, I think I remember that you write somewhere that this in the second topos, the object of random sequences has no points. Of course, the naive one has no points, but then even this one where you're independent of the measure one set you're supposed to lie in still maybe has no points. I'm not sure, but this definition seems relevant to ordinary probability theory too. So can we export this insight somehow in a way that non-topos theorists can use? And also the same question for other parts of the program.
So I did some work on a localic view of randomness a while back, and there was something to do with no points there.
That's what I was thinking of.
Yeah, so that's not actually the same thing as this topos. So it'll certainly be the case that the object of random sequences in this topos has no global points. So that is maybe related to what you're asking. And there's regarding the question of externalization, there's the whole topic of how to, so for example, I'm advocating, well, I think it's interesting to look at probability theory, especially from the viewpoint of this last topos. And then in the end, one would like to get some results saying, well, if one proves such and such a result in the topos, then it gives us this result in ordinary probability theory. So that would be a very good topic to look at, and I would like to do that in the future. At the moment, I've got a lot of stuff to do before I get to that. But yeah, that's a very good question.
Sure, thank you.
Thanks, Valeria. Do you have a question?
Sorry. Yes, thank you.
Yeah.
Very interesting, Alex. I know nothing about this stuff, so it's a completely ignorance question. But you said that one of the points of this work is not trying to deal with measure theory, right? It's kind of trying to abstract over the measure theory. Why is that a good thing? I mean, and second continuation on that is you also said that, it seems to me that you're taking the main two things that we want from probability, the business of independence of independent probabilities and invariance principle. So what else do you want so much? I mean, is it the stuff that Kevin was mentioning right now, kind of bringing back to traditional probability? Or, sorry, I haven't got what is it that you say that there's lots more to do, but what is this stuff that is more essential for you?
Oh goodness, well, that's quite a sweeping question. So
Sorry.
but let's just go back to the I guess the core question. I'm not trying to do away with measure theory at all. So measures are very important. In the last topos, I'm moving from sort of measures over some sigma algebra to what I call power set measures. So measures defined on all subsets. So that has the obvious advantage that you don't need to prove sets are measurable. I mean, of course, probability theorists are very used to proving that sets are measurable, but probability theorists use sigma algebras in a much more fundamental way too, which is they use sigma algebras for all forms of conditioning and sort of information dependency and this kind of thing. But from the probability theory I've read, I've found there's a sort of when you read probabilistic arguments, there's the uses of sigma algebras you can split into two camps. There's those which I would call bureaucratic, which are about checking that sets are measurable so that values are well defined, and those that are maybe one could say informative, which is about which is about the dependency of information and conditioning and things like that. And they tend to get very entangled with each other. So, for example, stochastic process theorists look at something called the standard conditions on a filtration, and these two aspects are kind of interwoven with each other in these kind of standard conditions that they consider. And according to what I'd like to try to do in my world is kind of get rid of the bureaucratic side, and the conditioning side, the informative side of sigma algebras, I believe, can be replaced entirely using functional dependencies between random variables, because which is particularly possible in this setting because random variables can be defined on arbitrary sets. So it gives you a whole lot of machinery that you don't have in ordinary probability theory for considering exotic random variables. So there was a lot more in your question, but I think maybe that's enough.
No, that's good. That's good. So it's not about externalizing the results that the probabilistic guys have. It's about kind of separating bureaucratic sorts of information from really informative ones. That's what you think that the pre-sheaves do for you. Is that it?
I think they get rid of the bureaucracy, the sheaves.
Yeah. Get rid of the bureaucracies. Separate so that you can get rid of it.
Yeah.
No,
If only we could sheafify the real world and get rid of the bureaucracy. That would be great.
Okay. No, thank you very much.
Yeah, thanks. So at this point, I'll stop the live stream. If the speaker and any audience members are available, we